Hi, everybody. Welcome back to our Hardy-Weinberg lab again. Um, so today we're going to look at question number 5 to see. I'll show you how I calculated it. Maybe if you watch me calculate this a little bit using the Hardy-Weinberg equilibriums, this may help you with the later question. So we'll tackle number 5 here together. You can kind of do it along with me, and I'll give you a couple of rules that you kind of have to follow using this, which are not really explained by the actual equilibriums themselves. So again, we're going to tackle number 5. So let's first and foremost review a little bit of Hardy-Weinberg. Number 1, we know that Hardy-Weinberg works really well if, one, there is, random mating going on, there is no gene flow. Number 3, no mutations taking place, which is kind of almost ridiculous to think about. Number 4, no natural selection, no environmental conditions that cause parts of the population to die off. And number 5, you have a small population, which here in human world and of even bacteria and stuff, that's not even possible. So interestingly enough, Hardy-Weinberg is good at predicting maybe some dominant recessive alleles in populations, but only in certain contained small populations, which really helps with maybe isolated areas where we see things or, say, species evolving differently than other places. For instance, birds, turtles, giant tortoises, evolving differently, say, on the Galapagos Islands compared to the mainland in South America, where there might be a larger population. All right, so let's go back over here. I think I created some notes on just the general Hardy-Weinberg equilibrium. Again, there are two parts to this. P plus Q equals 1, okay? And again, remembering that P is the dominant allele, Q is recessive. All right, couple little rules though first. When we calculate frequencies using Hardy-Weinberg, we always want to start with recessive first, because it is the one that expresses, it might be doomed for death or have a less frequency in the population. Why? Because we know that when we combine dominant alleles with recessive alleles, dominant always wins out over recessive. So in a homozygous dominant, obviously there's no recessive allele, so you're going to have the dominant trait. And say, for instance, in a heterozygous combination between, say, a dominant allele and a recessive allele, the dominant allele will, again, win out. So even though there's a recessive allele with that person, that means that they will still express the dominant allele. So let's take an example here. Let's say we have tall genes and short genes. And we'll say that capital T is dominant for tall, small t right here is for short, recessive. And the 3 different types of combinations we can have in this case will be homozygous dominant, capital T, heterozygous dominant, capital T, small t, and then homozygous recessive, 2 small t's. So this is where we have to remember that we always solve for Q recessive first. That's a rule of Hardy-Weinberg. Okay? Then we're going to use however we solve for Q, and at that point, then we can plug it into the other 2 formulas and calculate all of the other things. Alrighty? So hopefully that helps to explain a couple of ground rules for Hardy-Weinberg, kind of combining some of our knowledge of Mendel that we've talked about, and now Hardy-Weinberg equilibrium. Back to question number 5. Over here, let's do this. We'll maybe replicate this question over here to the side. So in this case, we know that we have, for number 5, we have 75% of our pop is dominant, 25% of our population is recessive. Now, it doesn't ask us to calculate how many members of this population. We could potentially if we said that there were 1,000 members in this population, but it's not asking us to apply it in that situation. So all we have to do is calculate the percentages, which is actually fairly easy. All right, so first things first, remember the rules. We have to solve the recessive frequency first. All right. So in this case, what we will do is we'll go back over here to our space. So we have a little more space, and we're going to say we're solving for T and T. Okay, so T is dominant, small t is recessive. All right, so let's think about what each of those things stood for in Hardy-Weinberg. We know that Q squared is the recessive homozygous recessive. And so to solve for Q, we're going to plug in our numbers here. We're going to say Q squared equals, okay, 0.2. So we know that 25% converts to 0.25. We will square root both of those to get rid of our factor here, our exponent. I'm going to square root this side as well because we got to balance the equation. And we are left with Q equals 0.5. All right, so that is for our recessive percent factor. Now, we have to solve for P. Solving for P means that we have to use the first part of the Hardy-Weinberg equilibrium. How do we do that? Well, we have to take the first part. It is, again, P plus Q equals 1. That's our equilibrium because we always solve for recessive first. So in this case, now what we're going to do is we're going to figure out what the factor of P is. So again, P, we just basically subtract. So we go is equal to 1 minus Q. We just moved it to the other side. Okay, now we'll plug it in. P equals 1 minus Q over here. Plug it in. 0.5 or 0.5. Okay, and then we just do a quick calculation. We know that 1 minus 0.5, P is equal to 0.5. All right, so now what we have is how we calculate each of these. So we have 3 categories. I'll zoom out here a little bit. So now we know what P, solve for P, the recessives, or I'm sorry, the dominants, and Q, the recessives. Alrighty, here we go. So now let's take a look at the Hardy-Weinberg equilibrium. P squared plus 2PQ plus Q squared equals 1. What do these all mean? Well, pretty easy. So all we have to do is say, all right, let's plug in, and we know that this P is going to be homozygous dominant, DT. So again, P squared, okay, all we're going to do here is go plug in what our factor was, 0.5. It's set to 1. So we just plug it in. This is equal to, not equal to, but it is equivalent to basically 0.5 squared. So hence, when we square 0.5, we know that is 0.25, and that means that 25% of our population is going to be homozygous dominant. Okay, back up here. We know that 2pq is both of the alleles together, so that means that it is homozygous, or sorry, correction, heterozygous dominant. So again, 2p q. All we're going to do is again factor in. So again, 2.5 parentheses 0.5. Multiply the two together. That gives us obviously 0.25. And this will equal 0.5, which is equal to 50% frequency of heterozygous dominant. All right. Here's our homozygous dominant frequency, heterozygous dominant frequency. Now we're going to look at the recessive. Pretty easy again. We know that homozygous recessive is q squared. And in this case, we don't even have to even really calculate, right? We know that it is 25% of the population, okay? Because we started with that all the way over here, right? So we know that q squared was going to be equal to 0.25. That's what we started with. So again, 25% of our pop is going to be completely recessive. The other 75%, this is how we divide them up between heterozygous and homozygous dominant. The reason we always start with the recessive is that we know that when the recessives combine together, they always express that recessive gene. However, when a recessive combines with a dominant, it doesn't express. Obviously, in a homozygous dominant combination, two capital T's, in that case, you don't have a recessive gene whatsoever. So what you always have to calculate is the first two, is where there is a dominant allele in the combination. So again, little review. We started off here knowing what the two percentages were. We knew that it was 75% dominant, but we didn't know, and what we had to calculate were these two things. And now that we know what they are, we know what the division is between them. So again, we solved for Q first, right here. Then we solve for P, and then we're able to solve for the other two percentages in the frequency between the three different pairings. And again, the three pairings that we can have of alleles are homozygous dominant, heterozygous dominant, and homozygous recessive. All right. Hopefully that helps. We'll zoom out here and everybody can see that. Hopefully that helps a little bit understanding, again, some of our general rules. Remember, you can always go backwards in this video, see how I solved and how I came up with some of the set rules. And again, these are rules of Hardy-Weinberg, all right, and some general rules of genetics, right? Dominant over recessive, not the other way around. Any questions? Please ask them questions. What I'd like you to do at this point now is take a look at number 6. See if you can answer number 6, calculating the frequencies, and you should be able to calculate number 7. And we will maybe look at number 8 together because there is one more step to this process. If you had a population of, say, for instance, in number 8, 200 plants, now you have to factor out that 200 between the 3 different percentages, which is actually pretty easy math to do. And you can do this with any population size. You just have to factor it out. All right. Hopefully this helps. Have a great night.